Hi guys, welcome back. You're watching the 8th lecture of EE635 Applied Linear Algebra, and this happens to be the third and final module. Before we ended the second module, we had posed a question which we had said is the one that we would be looking for, whose answer we would be looking for in the third module. And what was that question? The question was that so far we have seen that if there is a linear map between one finite dimensional vector space and another finite dimensional vector space, then there would be ordered bases for the two vector spaces, that is domain and codomain. And with the help of those ordered bases, we can represent the linear map as a matrix. Yeah, which together with the coordinate system for the domain and codomain vector spaces gives us a representation, yeah, of the linear map. Now the question is, if I choose different bases for this V and W, then I would get a different matrix representation for the same linear map. So although the linear map remains the same, the matrix representations are different. That's kind of unsettling, yeah, because the map remains the same. I have different matrices to represent the same map. How is that possible? Or even if it is possible, then is there some relation between these matrices? Yeah. So in this module, we're going to explore this relation between these modules, between these different matrix representations for the same linear map. Okay. So let me share my screen. Yeah. To make our life easier, we're going to restrict ourselves now only to linear maps from V to itself, from V to V, so that we don't have to play around with too many different bases, right? So think of linear operators now, but whatever we are doing can also be done for the general case of maps between different vector spaces. Only thing is that it is a little more complicated bookkeeping. Yeah, but there is nothing that nothing that that does not let these ideas to be applicable to the general situation as well. Okay, so consider linear operators, that is phi from V to itself. Okay, so I have a basis, say B is an ordered basis for V, and suppose B tilde is another ordered basis for V. Phi admits a representation in B. Suppose that is matrix A. This is going to be a square matrix now because it's from the same vector space to itself. We are assuming that dimension of V is equal to n, which is finite. And we also have phi in another basis, and suppose that's A tilde. This is also an n cross n matrix. The question is, how are A and A tilde related? Okay. Now, before we proceed, let us try and see this with a concrete example. Okay. So, suppose we are looking at the vector space that we believe that we understand the best. Yeah. So, and a simple illustrative example. Okay, so see this example carefully. Once you understand the example, the rest will come automatically, right? So, okay, what is the example? As I said, vector space that we believe we understand the best, R2 to R2. So there is a linear map phi from R2 to R2. we have already seen that this linear map can be represented by a matrix. Yeah. So suppose A is a matrix which is phi acting on E1 and phi acting on E2. Okay. This, let's say, is A, B, C, and D. What is E1? E1, of course, is 1, 0, and E2, of course, is 0 on the standard basis vector. We call it the standard basis for R2, right? Now, suppose for the same R2, suppose now I choose this basis, yeah? So this is my B. Now, suppose I choose a B tilde, which is these two vectors, yeah? Notice carefully, 1, 1, and 1, minus 1. This is also a basis, right? So now what we know, the same linear map phi under this basis will have the representation. So this phi in B tilde would be what? This is by definition phi's action on the basis vector 1, 1 and phi's action on the basis vector 1, minus 1, but expressed in the new basis, right? B tilde. This also expressed in the new basis B tilde. This would be the new matrix, which we are calling A tilde. Yeah. Okay. Now we understand this phi 1, 1 very much because it's just A must multiply 1, 1. But then that is representation of phi 1, 1 in the older basis, that is the standard basis. We need this one also. How do we get that? So this begs us to find out this particular idea that given vector V in R2, if I want to express this in the new basis, what should I get? How should I get this? Yeah, so let us try and explore that. So suppose we define this as alpha 1, alpha 2, or actually we don't have to define. Yeah, suppose it's alpha 1, alpha 2. Okay, how do I get alpha 1, alpha 2? What is the definition of alpha 1, alpha 2? This by definition is V alpha 1, 1, 1 plus alpha 2, 1 minus 1, the linear combination. So these are the coefficients for the linear combination that expresses the vector V as a linear combination of the basis vectors. Here we are interested in the new basis, so we're taking these two vectors. But now from that very old observation, this is nothing but 1, 1, 1 minus 1 matrix. By now you should be a pro of this observation, alpha 1, alpha 2. This is just the basis vectors written one after the other in the standard basis. This we call T, right? So keep in mind that this T out here is nothing but, so T is the new basis vectors expressed in the old basis. Okay, so notice that V is equal to T times V in the old basis, which then means V in the new basis is T inverse multiplying V, which happens to be V in the standard basis. So V expressed in the old basis when multiplies T must give me the, this just follows from the definition of this representation idea, the coordinate idea. Okay, in this case, this T happens to be this matrix. Its inverse also we can calculate, but let's not do this at this time. Now, so now we go back to our A tilde. What was A tilde? A tilde is defined as phi acting on 1, 1, its representation in the new basis, phi acting on 1 minus 1, its representation in the new basis. That should be A tilde, which is, now, how do I get this? I know phi 1, 1. Phi 1, 1 is, so phi acting on 1, 1 is A, B, C, D multiplying 1, 1, which is A plus C, B plus D is in the old basis. Phi acting on 1, 1 expressed in the new basis would be T inverse A plus C, B plus D. Here, phi acting on 1 minus 1 is A minus C, B minus D. Of course, phi acting on 1 minus 1 expressed in the new basis would be T inverse A, B minus C minus D. A minus C, B minus D. These are right. So A tilde then must be T inverse A plus C, B plus D. Yeah, this is the first column. Second column is T inverse A minus C, B minus D. Yeah, which is the same as pull out T inverse. Write A, B, C, D as before, and then notice that this is 1, 1, 1 minus 1, which is the same as saying this is T inverse A, T. So A tilde, that is the representation of the same linear map, the new basis is nothing but T inverse A, T. Yeah. If you notice carefully, this idea of representation of A tilde in terms of this idea of representing phi, the new basis, is nothing but chasing this commutative diagram, which is what? So notice carefully, what did we have? We had R2, R2. In the standard basis, I had this A matrix, which was taking vectors to vectors from R2, two vectors in R2. Okay. Now, from R2 to R2, there was this isomorphism, you see, using the new basis vectors. So this R2 is representation of the vectors in the new basis B tilde. Here also representation in new basis B tilde. And how was this related? This mapping in this direction was given by T inverse, and in the opposite direction was given by T, because you take a representation in the new system, multiply this by T, you get back old representation. What was this matrix T? If you remember, T was the matrix obtained by writing the new basis vectors side by side. Here also the same thing. This direction it was T inverse, this direction it was T. And this must be obtained A tilde, the representation of the same map in the new basis. This A tilde must be such that this diagram commutes, right? So then what will happen to a general vector? If I start from here and do this A tilde business, whatever I obtain must be the same as I start from here, the same vector. I now follow this path, and come back, I should get back the same thing, which means the map should be, see what is happening. A tilde then must be, A tilde acting on any vector, say x, must be the same as, take x, make t act on it first, that is this one. Yeah, follow this path. Okay, let me use a different color. Follow this path, that is t. Then follow this path, which is A. Then follow this path, which is T inverse. Yeah. So by just chasing the diagram, I know that A tilde must then be equal to T inverse AT, because this should be true for every x. This is true for all x, which then means A tilde must be equal to T inverse AT. That's it. Okay. Now, if you understand this much, you're done. What we are going to do now for the general case, yeah, for the general vector space, I mean abstract vector space, but once again linear operators only. You're not going to look at matrix, operators or maps, linear maps between different vector spaces. That you'll just think about it, and I'm sure you'll be able to do that yourself. What we're going to do now is extend this idea to linear operators on general finite dimensional vector spaces, abstract vector spaces. So we have phi, let me do it this way, for phi between V to, from V to itself, where V is a vector space over a field F, dimension of V is equal to n, which is finite. Okay, now we want, so we have a basis B and also a basis B tilde. Both are ordered basis for V. We want, suppose A is defined as phi expressed in terms of this basis, and A tilde is phi. I'm not writing two different bases here because because it's a map from V to itself, V to V. This has basis B, this has also basis B. Yeah, same basis. Unlike before when we had BV and BW. So the matrix representation dependent on both the bases. Here I'm assuming that the bases are same. But I have, for both these cases, I have B and B tilde. So this is the representation of the linear map when V has basis B. So we start with coordinates in B and see how A acts, and coordinates in B tilde and see how they act. A and A tilde are those two representations. So once I draw the diagram that we have to chase, it should be clear. So what the situation is, V here, phi, there is the identification through B. This gets mapped to Fn, this identification. Let me not draw this both arrow because then it's kind of confusing. Instead, I draw this direction so that it's clear. This is also via B, F to the N. This diagram chasing gives me A. This is an isomorphism. Yeah, we have seen before. Similarly, I have an isomorphism from here, another two isomorphisms, but this is done in the new basis. And in the new basis, once again, following the same logic, I have this representation, A tilde. Here, this is the whole commutative diagram. The question is how A and A tilde are related. What is the relation between A and A tilde? That's what we have to find out. But see, this is exactly the same situation as before when we did this with R2. Only thing is that there's this V sitting in between. So why don't we just get rid of this V, yeah, and obtain this diagram instead. From here, we obtain f to the n, f to the n, f to the n, f to the n. Here is a tilde, here is a. This is going to be an isomorphism. Why? Because this is the composition of these two isomorphisms. Yeah. Here is one isomorphism, here is another isomorphism. Compose them, you get another isomorphism. Another compose them, you get another isomorphism. So these two are the isomorphisms that we need to figure out what they are. Once we do that, they're done. Right? Now see how this isomorphism works. So let us look at this one. This one. So suppose I start with an arbitrary vector here, x. Yeah. Say this x is alpha 1, alpha 2, up to alpha n. This n tuple. This x gets uniquely associated with a v here. What is that v? That v must be alpha 1 v1. Okay, before we start, yeah. So, sorry. B is v1 up to vn, and b tilde is v1 tilde up to vn tilde, two different bases. So from that it follows that this is nothing but alpha 1 v1 plus dot up to alpha n vn. But then if I go to this v and follow this map, I should come to some y, and what this y should be. So suppose the same v is expressed as beta 1 v1 tilde plus dot up to beta n vn tilde, then this means y, which is v's representation in the new basis, and this must be beta 1 up to beta n. The question is how beta 1 up to beta n and alpha 1 up to alpha n are related. So the question is how to get this map. Yeah. Now, notice. Suppose, so because v1 up to vn is a basis, v1 tilde must be expressible as a linear combination, v2 tilde must be expressible as a linear combination, so on up to vn tilde must be expressible as a linear combination of vectors v1 up to vn, that is basis vectors in the old basis. So let us try and do that. Suppose v1 tilde expressed in the old basis b, expressed in the old basis b happens to be T11, T21, up to Tn1, right? V2 tilde in B is T12, T22 up to Tn2, and so on up to Vn tilde B is equal to T1n, T2n, up to Tnn, like this. Yeah. What does this mean? This is equivalent to saying V1 tilde is the linear combination Tj1 Vj, j going from 1 to n. This is the same as saying, like before, it's like kind of tedious. It becomes tedious after a point of time, but we have to do it. Tj2 Vj. I'm just expressing the vectors in the new basis as a linear combination of vectors in the old basis. Yeah, how does that help? That helps us here. You see, V was beta 1, V1 tilde plus dot 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 up to beta n Vn tilde, yeah, which is the same as now beta 1. This I will write as this linear combination as we have done before. This is T j1, j going from 1 to n, Vj plus beta 2 summation j going from 1 to n, Tj2 Vj plus dot 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 plus beta n summation j going from 1 to n, Tjn Vj. I'm just like before, just like in the second module, I'm going to club these V's together, all V1s together, all V2s together, and so on. For that, this will help. This is nothing but beta 1, T11 V1 plus T21 V2 plus dot 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 up to Tn1 Vn plus beta 2 T 1 to V1 plus T2 to V2 plus dot 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 up to T2, sorry, Tn to Vn plus dot 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 plus beta n T 1 n Vn plus T2 n V2 plus dot 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 Tn n Vn. I'm going to club all V1s together. This is okay. T11 beta 1 plus T12 beta 2 plus beta 2 plus dot 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 T1n beta n, this into V1 plus T21 beta 1 plus T22 beta 2 plus dot 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 up to T2n beta n V2 plus dot 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 plus T okay, n1 beta 1 plus T n2 beta 2 plus dot 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 plus T n beta n into Vn. Right? This is an expression involving V1 up to Vn, and this is also another expression involving V1 up to Vn. Because these expressions have to be unique, because V1 up to Vn is a basis, that means alpha 1 up to alpha n as a column vector must be same as the column vector that I obtained by stacking these coefficients one after the other, which then tells me that alpha 1 dot 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 up to alpha n, this n tuple must be equal to T11, T12 dot 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 up to T1n, T21, T22 dot 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 up to T2n, Tn1, Tn2, Tnn, beta 1 up to beta n, which is the same as saying x is equal to t times y, where this T matrix now is these entries, right? T11, these entries. But how did we get that? Look at the first column, T11, T21 up to Tn1. That first column is V1 tilde represented in B. Look at the second column. Second column is this one, which happens to be T12, T22, and Tn2, which is V2 represented in B in the old basis. So that means T is nothing but V1 tilde expressed in the old basis, V2 tilde expressed in the old basis, so on up to Vn tilde expressed in the old basis. Write this down as columns. The matrix that you get is T. So let us redraw our this was A tilde. This is F to the N, F to the N. This is A. This is in the original basis. This is in the original basis. This is in the new basis. We chose an arbitrary vector X here, and we wanted to find out how this gets mapped to the Y here. This, we have seen that X is equal to Ty. So in this direction, the map is T inverse. So in this direction, this map must be T. Sorry. Just the opposite. Yeah. In this direction, from Y to X, we have to multiply Y by T to get this X. So this must be T inverse. Because this is a basis, we want up to V, we want tilde up to V and tilde is a basis. This matrix must be invertible. Yeah, here also we do the same thing. In this direction, this is T. In this direction, this is T inverse. Yeah. So you see, by commutativity, we must have, so I start with X. So AX must be the same as, you take X, multiply T inverse first, and then multiply A tilde, and then do a T. This is true for all X, because X was arbitrary. So this implies A must be equal to T A tilde T inverse, which is the same as A tilde must be T inverse A T. Yeah, so more elaborately, phi in the new basis and phi in the old basis, they are related by T inverse AT, where this T is what? T happens to be the matrix that is defined by V1 tilde in the old basis, V2 tilde in the old basis, sorry, Vn tilde in the old basis, written as columns. That's it. That's the trick. And in linear algebra language, this way of getting one matrix from another is called similarity transform. Similarity transformation on a matrix. So what does that similarity transformation matrix, similarity transformation on a matrix tell us? It tells us that similarity transformation gives us a matrix which is the same, which is a different representation of the same linear map, which has happened because a new basis has been chosen. Yeah, this is called change of basis, and that is why the popular myth in linear algebra which says that similarity transformation is just the result of a change of basis. That's it, nothing else. So it's the same linear map. So two different matrices may actually not be different. As maps, they may be the same map, just being represented in different bases. We will have to say so many more things about similarity transformations when we look at eigenvalues and eigenvectors, minimal polynomial, characteristic polynomial, canonical representation of linear maps and so on. Okay, and there this similarity transformation will play such a huge role. Okay, but we'll have to wait for that. That will come post midsim. So I hope this lecture was understandable. If there are any questions, feel absolutely free to post those questions either to as either as comments on the YouTube video, or post them as questions in the stream in Google Classroom, or you can send posts on Moodle. You can also directly send mails to me. Okay. All right, so I hope you guys are doing well. So stay safe, stay healthy, take care, and bye bye.